Welcome to Week 9. This week we extend the work we have done in the last week or so on partial regressions, and we look at what's called the negative binomial regression. So this is a slightly different new model here, and we will see why we need this model in the case of the Poisson. So there's a little bit of mathematics here, but it can be largely ignored. It's for those who understand the mathematics and might be interested in it. So the Poisson regression we saw earlier is for count data, where you model the counts as Poisson distribution. The only parameter there is the lambda, which is the mean number of occurrences over the appropriate volume in this case. And so the values that the Poisson distribution takes are simply 0, 1, 2, 3, and 4, and so on. And further, the distribution or the probability mass function is given by this expression, so it's e to the negative lambda, lambda to the y, and y factorial. And we know from here that the mean of the Poisson expected value of y is equal to lambda, and also the variance of y here for the Poisson distribution is also lambda. So the Poisson is one of those distributions, just about the only distribution that has a mean and variance that's equal here. Now what happens if the mean or the variance isn't the same as the mean? If the variance is less, we say the model is under-dispersed. If the variance is higher than the mean, then we say the model is over-dispersed. So those are the two problems we'll find with the Poisson model. So we'll see later, towards the end of the lecture, how we can test for this, whether the model is under-dispersed or over-dispersed or correctly dispersed. And so as we saw here, essentially the idea is that if the model is not appropriate, the Poisson model is inappropriate because the model is over-dispersed, then we require another model, some other suitable model that actually is more dispersed than the Poisson, something that has a higher dispersion than Poisson here. And if otherwise, what we'll find is that the Poisson regression doesn't fit the data very well, because the variance is increasing faster than the mean. And so that would mean that the model doesn't fit very well, and you can see this from the piece of the suitable plots where the variance just blows up as the mean increases. But as I say later, we'll take a look at the some formal tests of this as well. So the negative binary distribution arises from this here. We have y as the usual Poisson distribution with our parameter lambda, which is the mean and the variance here. And but lambda is also a random variable with the gamma distribution. Now, if you haven't seen the gamma distribution, don't worry too much about it, because, as I say, the math says for those who might have met these things and are more interested. So, y is a Poisson distribution given a parameter lambda, and the lambda here is a gamma distribution. Now, the gamma distribution is a continuous distribution, because the mean here, of course, for the Poisson is continuous, and it takes the probability distribution function here, PDF here, is beta to the lambda, and this is the gamma function here on the bottom, gamma function with the parameter lambda. Then it's lambda to the alpha minus 1, and e to the negative beta lambda for lambda bigger than 0, and otherwise it's 0. And here the mean of the gamma distribution is alpha upon beta, and the variance is alpha upon beta squared. Now, this gamma function here is sometimes called the generalized factorial function, because for integer values, gamma of n is n minus 1 factorial for positive integer values. And otherwise, it's actually defined as gamma z is the integral from 0 to infinity of t to the z minus 1 e to the negative t dt. Now it says here is defined for all complex numbers. So those who have the higher mathematics will understand what that means. In fact, we're looking at a complex function here. And of course, the idea here is that the number z here must have a positive real part, otherwise things go crazy as far as the actual convergence of the interval is concerned. So this is all the mathematics behind it. But as far as we're concerned, we'll deal with the model fitting only. So y here in that case has a distribution that looks like this. First of all, we have the Poisson part, and then we have conditional on that the gamma part, so that the distribution of y and lambda together, the joint distribution, looks like this. Okay, now so the negative binomial distribution is the unconditioned distribution. This we obtain here probability of y equals y, which actually means we take a look at the joint distribution for lambda and for y, and we integrate out the lambda here. Rather complicated. So we don't have to worry about this, but actually it comes down to this kind of expression over here, as we've got here. Probability of y equals y becomes this kind of expression. You will see something to do that looks like a binomial distribution here, and similarly here it looks like binomial as well. In fact, these two probabilities add to 1, and you've got the alpha and the y here as well. So there's little bits of binomial things in there, but it's not quite binomial. It's called negative binomial for a reason that we might see later on. So here again, y takes integer values starting from 0, positive integer values, or non-negative. And so this is, in that case, suitable for modeling the Poisson distribution. So here again, the mean, as we saw earlier, is similar. E of y is alpha upon beta, and the variance is the alpha upon beta squared from before, but there's also the mean part here. So this part actually comes from the Poisson distribution, and this part comes from the gamma distribution. There's two parts to it. As you can see here, that looks a little bit more. So the variance actually is a bit larger, and that accounts for the over dispersion over here. Now, as you can see where, if I put alpha is equal to beta lambda, and if beta goes to infinity, then the negative binomial distribution approaches Poisson distribution. So if I put the alpha as beta lambda here, you can see that if I put this as beta lambda, you can find the betas cancelling off over here. But here, of course, when the beta goes to infinity, the whole thing goes to 0, and I'm left just simply with this alpha, this lambda as our variance here. And the same here, then the variance here, the mean here becomes lambda as well if I put alpha as lambda beta. Now, there are many ways to parameterize this negative binomial distribution, but the one we're looking at is simply this essentially. So we've got here that mu is equal to alpha upon beta and theta is equal to alpha. With that parameterization here, the mean is simply mu, and the variance is again mu plus this extra bit over here. And the extra bit here will go to 0 if theta goes to infinity. We're going to approach the Poisson distribution. And so, because of this extra plus term over here, the negative binomial can accommodate over dispersion in the Poisson model. But note, it can't handle under dispersion because there's an extra positive term that's added on here. It can allow for a variance larger than the mean, but it can't allow for under dispersion. That's altogether a different problem. So here's the probability mass function, not of great interest to us, but still just for those, as I say, who are interested in the more mathematical part of it. So we write this as y is negative binomial with the two parameters mu and theta. Now, here's some plots to see what's going on. Here's the Poisson distribution plots here for lambda equals 1, 2, 3, 5. And note here, as we said earlier, the D here, so the basic command for Poisson is POIS in R. And the first determines what's going on. So D is for distribution, P is for probability, R is for random simulation. So here is a plot of this. You can see as lambda increases, the distribution becomes more and more symmetric. Now, of course, here the lines are joined, so you can see some shape over here. But essentially, this is actually just discrete, so we should just have the dots here. But the lines are joined, so you can see the kind of distribution, or the shape of the distribution we get for various values of lambda. Now, if you do a similar thing, and you can look at the R code afterwards, we do a similar thing for the negative binomial distribution, we get this kind of plot over here. It looks similar in many ways to Poisson. And so, but you can see here, it's just got a bit of a wider tail, a longer tail here in that sense. Look at the earlier example here. The Poisson dies down quite fast over here. As you can see for the early values at least, it dies down quite fast and goes towards 0 very fast. But if you look at the negative binomial, it takes a while to get to 0 and goes more slowly here. So this is making sense to us because we did say we're going to allow for a larger variance. and the larger variance here you can see in the longer table. Example here we'll take a look at. This is from the UCLA Institute for Digital Research here, where we're taking a look at the attendance behavior of high school students here at 2 schools. And the predictors for the number of days absent is what we're looking at. This is our response here. It includes the type of program in which the student is enrolled and a standardized maths test as well. And so the attendance we've got here for 314 students here. And the count, as I say, is for the number of days absent. The response variable is available in days absent. And the variable maths gives the maths mark. And the variable program, prog, gives the 3-label nominated variable indicating type of instructional program here. So we can take a look to see what's going on here. We've got the data here. What we've done is we've defined the program here essentially not just by the levels 1 to 3, but given it names here: general, academic, and vocational. And we have made the ID into a factor because ID is just the number 1 to 308. So gender here is just, as you'd expect, male, female, maths mark, days absent, and the program. Now, gender actually is just, in this case, should be, as I say, male, female, but here you find it's actually 1-0. Not that it matters here, we'll see how it works out. So here, straight away, by looking at some plots over here of the data, some histogram essentially of the data itself, we can see pretty clearly this is the lowest mean. Number of days absent. Lowest mean the number of days absent. The other two are higher. Exactly which is the highest we can't so easily tell from this plot here, but by taking a look at some statistics here we can see pretty quickly. We're using the t-apply function over here. That will be familiar to you here, but what might not be familiar is this extra command sprintf. So this sprintf is a C-style print command in R. So if those who have done C will know this. C has just a printf command here. So the first part is telling us some text and formatting. So we're going to have the number the M and SC printed out here, and it's going to be 2 decimal places, and the SD also in brackets 2 standard decimal places. And with the median standard deviation in those places to be printed out, you can see what's going on here. So we're printing this for the days absent here by program here, and the function is this sprint function. General has the mean of 10.65, that is the highest mean, and the standard deviation of 8.2. Academic has mean of 6.93 and standard deviation of 7.45, and then vocational. So we know vocational is the lowest, and it looks to be very much lower than the other ones. Whether general and academic are the same or not, we don't know yet, but the model will tell us. So it certainly shows that the program style is associated with the number of days absent here. We can fit our model here. So we used GLM for the generalized linear model for the Poisson, but now we're going to use GLM.NB for the negative binomial. And notice there is no need to specify a link function because the NB tells us it's a negative binomial. There is no other link required here. But this GLM.NB function resides within the mass package, so you must load that first. So library mass first, then the usual model specification is GLM.NB. Days absent is our response variable, and the other variables are the maths and the program. Now, actually, we can also use here gender. We can add that to this as well, and we'll see how that works out later. And so this is all we require. Notice how this looks as well. I've got the object M1 that is associated with the model, but I've got brackets all the way around, so it gives me the summary as it runs the command. And here's the summary. We've got maths and program now. This is the generalized linear model for the negative binomial distribution, or negative binomial model here. And so there's the model here, but you find it actually gives the initial theta value. It requires initial value here to start the actual iterations for the calculation of the parameters. So it chooses initial value of theta based on some calculations it does inside. You can look at the details if you like online. Now, looking at this, we find that certainly maths is important here. A higher maths score means a lower number of days absent, is a negative coefficient. Academic is a negative coefficient, and vocational also is negative. So this is being compared with the first level. If you go back a second, you'll find what the first level was. We had here the levels of general, academic, and vocational. So here we have got academic and vocational. So our reference here is general. Program general is our reference here. So we can see compared to general, academic has a lower mean and vocational also has a lower mean. And it won't take you very much to work out the fact between vocational and academic. The difference is about 0.8 here, and the standard errors are to about 0.3. So about roughly speaking, you can find that also vocational has a lower mean than the academic program. Now it gives you the dispersion parameter as 1.0327 and it's taken to be 1. It's not different from 1, so we can accept it's okay. And it also gives you the actual estimate of theta, which is 1.033, not very far from the initial estimate here. So, variable maths has a regression coefficient of negative 0.006, which means it's significant. And so for each unit increase, 1 unit, whatever it is, because this was standardized, remember, for each unit increase in maths, the expected log count, for the number of days absent decreases by 0.06. Now, gender was not fitted over here. Now, in fact, gender should be converted to a factor first, but it's not significant in the model, so we're not going to bother with it. You can try that yourself later on. Some spelling errors here should be note, and should be not. Overall, this is our finding here. The program academic is the expected differences in log count between this group and the reference, which is general. Likewise, for the other one, which is vocational. So we find that the academic program on average has a 0.44 lower than the expected log count for vocational. So the expected count for program academic is 0.44 lower than the expected log count for program general. And likewise, if you look at vocational and general, you find that vocational has a lower log count compared to general here. Now, if you want to determine if program itself overall is statistically significant, we can compare model with and without prog. And we can do that. And so the reason here is it's important to fit separate models that unless we do, the dispersion parameter is held constant. So here we can see program is significant, but to test this, we should fit the model without program. If you do that here, and you then compare models, you find that program is significant, statistically significant here, and between those two models here, it doesn't necessarily hold. You can see the theta value changes between those two, so it doesn't necessarily hold or keep the same dispersion parameter. And so certainly here, by looking at those p-values here, you can see that program is a significant variable in the model. Now, what if you can actually compare this with a Poisson model? So if I fit the usual Poisson model here with maths and program as our variables, and the family is Poisson. Now, here we are actually going to test to see if the model is correctly dispersed. And the library AER has the function we require, which is simply dispersion test for the model which we have fitted. The model object is M3, and the alternative here is two-sided. We don't have any idea whether it's under dispersed or over dispersed, so we'll just make it two-sided. But looking at this here, the outputs here, you can see that the dispersion parameter here is actually 6.5. The p-value is rather small here. So certainly in this case, we will reject the null hypothesis that the dispersion parameter is equal to 1 and conclude it's not equal to 1. Since this actually, the value here is bigger than 1, we conclude the dispersion parameter here is bigger than 1. So that makes this particular data suitable for the negative binomial distribution or negative binomial model. And below, all you've got is just extra likelihood tests, looking at the degrees of freedom here appropriately, and looking at the log likelihood for the dispersion parameter here. So here, what we know is dispersion test shows that the Poisson model is over-dispersed. The chi-squared value here is 926 with 1 degree of freedom. So this is for the particular test there. And we have a very strong evidence here that the negative binomial is a better model than the Poisson. We can actually predict the number of edge absent here by looking at confidence intervals. So here we're looking at the confidence interval for each of those. Now what we're doing over here is it's exponential, because remember this is logs we're looking at. It's the log number of edge absent. So we take a look at the confidence interval for the particular estimates, and then we take a look at the exponential for those. So these are the actual confidence intervals for each of those estimates. So the mean number of days absent is 0.99, and program academic is 0.64 and 0.27 here. And here the confidence intervals appropriately for that. So overall, we see that the incident rate for academic program is 0.64 times the incident rate for reference group. Because remember how it works out here, by taking exponential, it becomes a product. So it's 0.64 times the mean for the reference, which is general. And vocational, it's 0.28 times. So in both those cases here, academic and vocational have lower incidence rates or lower days absent compared to the reference, which is general. And for percentage change in the incidence rate of days absent is 1% for every day increase in maths. So if you look at this here, maths is 0.99 times, so every extra unit of the increase in math mark gives you a number of days absent as 0.99, which means that's a decrease of 1%. And finally here, we don't recommend that the negative binomial be applied to small sample sizes, because in fact in small sample sizes you often can't judge anyway whether the model is over dispersed or not. And the other problem we saw last week was the problem of excess zero, or the zero inflated Poisson model. They are separate models for those altogether, and we won't look at them here at all. We might look later in the course whether we discuss this model, but this is more advanced material which we will not look at. If you're interested, you'll find lots of material online, and there are programs that actually allow you to model those kinds of data. The other end is when we have no zeros at all in the model, in which case we're looking at what's called a zero truncated Poisson model. And of course, the outcome can never be negative in any count data modeling situation we look at. That's all for this lecture. We will see you next week. Thank you. Bye.